a little bit longer?
Yeah, just a moment.
Okay, sure.
Yes. So, welcome to the last talk of the day. We have Peisi Huang from University Nebraska, and she's going to talk about dark matter during first order phase transitions.
Yeah, okay. Yeah, thank you very much. Yeah, I would like to thank the organizers for the invitation. I'm sorry. Okay. Yeah, I would like to thank the organizers for the invitation. So I'm not going to motivate dark matter or first order phase transition. So let me jump directly to it. So I'm going to talk about how phase transitions can change the properties of dark matter, and also I'm going to discuss briefly how we can produce dark matter in a way from first order phase transitions. So I'm going to talk about the abundance. I'm going to talk about how a first order phase transition can change the dark matter relic abundance. So the usual story is the following. So we have the WMAP and Planck space observatories. They have measured the dark matter relic abundance extremely well, and the measured value is about 0.12. And then from the particle physics side, for a given particle physics model, we can calculate the dark matter relic abundance by solving the Boltzmann equation. And in practice, we often do change of variables and have the equation in terms of the yield, and which is defined as number density divided by entropy, and what we call X, which is defined as m over temperature. So this is the usual thermal phase-out picture. So if we have a larger annihilation cross-section, that means the annihilation is more efficient, and therefore we expect smaller relic abundance. So in this plot, all three lines corresponds to the same annihilation. All three lines corresponds to different annihilation cross-sections. So annihilation cross-sections increase from 1 to 3, and therefore we see smaller relic abundance from 1 to 3. So that means for a given dark matter mass, we expect a magic number that gives the right relic abundance. And for WIMP dark matter, this magic number is about 10 to the minus 26, which sets a target for indirect detection experiments. So in this work, the authors conducted a model-independent study on the parameter space, which is constrained by dark matter indirect detection experiments. And what they found is the following. They found that this green region is excluded by indirect detections, which they call visible, and then they find the purple region is excluded by unitarity bounds, which they call unitarity. So the region here is the overabundance, and we have a very narrow WIMP window, which is this orange line. So for now, I'm going to focus on this white triangle where the thermal dark matter is underabundant. And I'm going to ask the question, can models with higher cross-sections yield the observed dark matter abundance? So to answer that, let's go back to the Boltzmann equation. The Boltzmann equation is a first-order differential equation, and a first-order differential equation requires one boundary condition to solve. For the thermal phase-out picture, the boundary condition is very simple. We say early on the dark matter abundance tracks its equilibrium number. So one way to change the solution of a differential equation is to change the boundary condition. So here in this plot, we plot the relic abundance, the solution to the Boltzmann equation with the same annihilation cross-section for all three lines, but different boundary conditions. The purple line is the usual thermal case, and for the blue line, the dark matter is produced later than the phase out, and the initial abundance is higher compared to the thermal case. And then we got a larger relic abundance today. And then for the yellow line, again, it has the same annihilation cross-section, but with a smaller initial abundance, and therefore we end up with a smaller relic abundance today. So the basic idea here is that we want to save those underabundant dark matter models by modifying their boundary conditions. So we have the dark matter produced later after the freeze out. So this idea has been explored in the literature, often referred to as delayed production. So the idea is the dark matter does not exist early on, but it is produced by the decay of some heavy particles like inflatons or moduli fields. So in this work, we consider another possibility of producing the massive dark matter. So here we consider producing them through a first order phase transition after its freeze out temperature. So to do that, we couple the fermionic dark matter fields chi to a scalar field phi through a Yukawa interaction. And the scalar field phi undergoes a strong first order phase transition. So I'm not going to specify the underlying particle physics model for the phase transition here to keep the discussion more model independent, and you can feel free to put in your favorite model here. So this chi, the fermionic dark matter field, is massless before the phase transition, and it acquires the mass of m, which is y v phi after the phase transition. So in this way, we produce the massive dark matter during a first order phase transition. So to estimate the relic abundance, let's go back to the Boltzmann equation. So the phase transition happens after the freeze out. So dark matter has already fallen out of equilibrium. So the equilibrium contribution can be ignored. So I'm going to ignore this term. So the final relic abundance is a competition between the expansion of the universe and the annihilation. So we define a critical number density by equating the expansion and annihilation rates to track the effect of those two terms. And we consider the following two scenarios. In the first scenario, the number density at the production or the number density at the time of phase transition is smaller than the critical number density at the phase transition. So that is shown in this yellow line. So in this scenario, the expansion of the universe dominates over the annihilation. So that means the relic abundance is already frozen. So in a sense, it's not a very interesting scenario. Something more interesting is this is the scenario that we show in this blue line. So the number density at the time of the production or at the time of its transition is higher compared to the critical number density. And in that case, that means the annihilation dominates over the cosmic expansion. And therefore, we expect rapid annihilation until the two rates are equal and the dark matter number density begins to stabilize. And after a quick calculation, we can show that the final abundance is the thermal relic abundance times the ratio of the freeze out over the phase transition temperature, or the temperature in which the massive dark matter is produced. So that opens up the parameter space significantly. So let's go back to this plot and again focus on this open triangle here. So for thermal models predicting underabundant dark matter, they can be fixed by a delayed dark matter production. And for every point in this open triangle, we have the mass and the annihilation cross-section. And we can calculate the corresponding production temperature or the phase transition temperature for an enhanced dark matter abundance to match the observed 0.12 value. So again, we use, oh, sorry. We use this equation right here. So the abundance is enhanced by the ratio of freeze-out temperature divided by phase transition temperature. So we found that typically mass of the dark matter mass over the phase transition temperature is typically in the range of 100 to 10,000. So now we can discuss the signal. So one good thing about this scenario is we can have signal from both phase transition and dark matter. So we have a strong first order phase transition, so we expect the gravitational wave backgrounds. And to calculate the gravitational wave signal, we need 4 parameters. We need alpha, the strength of the phase transition, beta, which is the inverse duration of the phase transition, T phase transition, which is the temperature of the phase transition, and the wall velocity. So once a particle physics model is specified, all those 4 parameters can be calculated from the model. But since we did not specify a model here, we are going to treat those 4 parameters as free parameters. So the gravitational wave signal is proportional to alpha over 1 plus alpha squared. And as we have shown here, in this scenario, to have the right relic abundance, typically we require m over phase transition temperature to be in the range of 100 to 10,000. So that implies the phase transition is very strong. So alpha is much larger than 1, and therefore we saturate this ratio. And then the phase transition temperature, as we discussed, is determined by the mass and annihilation cross-section to match the right relic abundance. And then for the wall velocity, we need to be in this blue scenario. So that means the dark matter relic. So that means the number density at the time of phase transition is higher than the critical number density at the time of phase transition. So we know the number density of dark matter in the in the symmetric phase, and we know the minimum number density we need in the broken phase. So that sets a lower bound of the penetration rate, and that in turn sets a lower bound of the wall velocity. So then this wall velocity, the minimum wall velocity is determined by requiring enough dark matter is produced in the true vacuum. That leaves us with only one free parameter, this beta parameter here, the inverse duration of the phase transition. So we take points from this open triangle and in the dark matter parameter space, and we calculate energies and frequencies of the peak gravitational wave signal. And we have one free parameter beta here. So different islands corresponds to different value of beta over h. So for lower beta over h, say beta over h equals 1, the peak frequency is in the range of 10 to the minus 7 to 10 to the minus 3. So the lower end can be probed by the pulsar timing arrays like Gaia and Sia. And then when we increase beta over h to 100, we mostly fall into the Lisa range. And when we further increase beta over H to 10 to the power fourth, we move more to the range of ALEA, D signal, and BBO. And the signal is weaker when we increase beta over H to 10 to the power 6. So we see in most cases, the gravitational wave signal peaks are well within the proposed and upcoming detector's sensitivity. And also, we have another probe from dark matter indirect detection. Here we plot the upper bound from tau plus tau minus. So the current exclusion line is from Hess, and we also have the future experiments from CTA. So the good, as I mentioned, the good thing about this model is it allows the probes from different experiments. So here the disks are the points which is allowed by Hess, and the one we cross out are the one that are not compatible with Hess. And the one we outline them with those black outlines are the ones within the CTA sensitivities. And the color bands are the sensitivities, sensitivity ranges for the some selected gravitational wave interferometers. So we have Sia and Lisa and Aliyah and ET here, but for each frequency range, there are different experiments. So the key point here is there is a very nice complementarity between gravitational wave interferometers and dark matter indirect detection experiments. So the gravitational wave can probe the dynamics of the phase transition, and the indirect detection can constrain the annihilation of dark matter. So now let's talk about overabundant. So let's go back to the Boltzmann equation. We want to change the solution of this differential equation. We just talk about changing it by changing the boundary condition. And another obvious way is we can change the annihilation cross-section here. So the idea we're trying to explore here is the annihilation today. So the annihilation cross-section we put in here is the one that can be probed by indirect detection, and that is the annihilation cross-section today. So what if the annihilation cross-section today does not equal the annihilation at the freeze-out? So the idea is the following. So we have the dark matter annihilate very efficiently early on, which set the relic abundance. And then a phase transition happens. After the phase transition, the annihilation cross-section is highly suppressed. So, and therefore, naively, we would expect the dark matter to be overabundant. So to discuss this scenario, we consider a dark photon model. We consider a dark photon that has a kinetic mixing with the standard model gauge boson. So we have this term right here. So if we have very small kinetic mixing, or if we have a heavy mediator, then we expect the annihilation cross-section to be very small today. And then if we infer from the indirect detection naively, we would say the dark matter is overabundant. So the question we are asking here is, what if the dark Higgs undergoes a phase transition? Then the story is the following. Early on, the universe is in the symmetric phase. Dark photons are massless. And at that time, the annihilation is dominated by psi to dark photon, dark photon. And we can write down the annihilation cross-section as GD to the power fourth divided by m dark matter square. So here there is no kinetic mixing or the mass of dark matter, the mass of the dark photon. So that means this cross-section can be large. The annihilation can be efficient enough. So if the dark Higgs phase transition happens after the freeze out, we can get the relic abundance. So the key point here is the relic abundance is set at the symmetric phase rather than at the broken phase. So now let's talk about phenomenology. For a given dark matter mass, we can calculate the dark gauge coupling by requiring the right relic abundance. And then some other constraints comes from we need to require the dark sector to be in thermal equilibrium with the standard model particles, and that sets a lower bound on the kinetic mixing for a given mass of dark matter. And then we want to have different channels, different annihilation channels in the broken phase and the symmetric phase. So we put the dark photon mass to be slightly above the dark matter mass so that the dark matter to pair annihilation to a pair of dark photons is kinematically suppressed in the broken phase. And therefore, in the broken phase, the annihilation is dominated by the annihilation through an off-shell dark photon to a pair of fermions. So what we find is that to get the right relic abundance for dark matter that is naively overabundant by 8 to 11 orders of magnitude. So again, we can have the gravitational wave signal. So similar to the previous case, we have those two free parameters. And for this scenario to work, the phase transition temperature is below the freeze out. So we set the phase transition temperature to be the freeze out temperature divided by 3, which is about the dark matter mass divided by 100. And similarly to the previous case, we expect pretty large alpha, so we saturate this alpha to alpha plus 1 squared ratio. And with large alpha, we expect the wall velocity is close to 1. So again, we only have one free parameter, the duration of the phase transition. So this time, instead of using that, we use something equivalent, which is the mean bubble separation. So with that, we plot the gravitational wave signal. So different lines are for different R star, H star. So the blue is for R star, H star equals 0.1. Red is R star, H star equals 10 to the minus 2. And green is R star, H star equals 10 to the minus 3. And different panels here are for different values of dark matter, which sets the phase transition temperature. So again, we expect the gravitational wave signal can be probed by upcoming experiments. There is one particularly interesting region where the dark matter mass is within the range of 1 to 10 GeV. So in that range, dark matter annihilates into electromagnetically interacting final states. After recombination, inject energy into the primordial plasma and leaving observable imprints on CMB. So in this range, there is stronger constraints on the annihilation cross-section. So the typical 3 times 10 to the minus 26 number cannot work here. So the canonical value is excluded, and there are discussions in the literature about how to make things work, how to satisfy the constraint while getting the right relic abundance. And here we provide another way to suppress the late time annihilation through a dark phase transition. And in our setup, we set the phase transition temperature to be the mass divided by 100. So for 1 to 10 GeV dark matter, we expect the phase transition temperature to be between 10 to 100 MeV. So that is interesting in another sense because it provides a viable fit to nanograph. So here different lines are for different mass of dark matter. So we see we can get reasonable fit for the 5 GeV, which is the red line, and 10 GeV dark matter, which is the purple line here. So for 5 GeV dark matter, the peak frequency is within the observable band of nanograph. The signal is slightly on the higher end for lower frequencies and slightly on the lower end for higher frequencies. And then for the 10 GeV case, which is the purple line here, the peak frequency is higher, so the signal is slightly on the lower end for lower frequencies. And for low mass of dark matter, which is, say, this blue one, the 1 GeV dark matter, the peak frequency is in the middle of the nanograph band, so it cannot really give a good fit for the high frequencies. And for the heavier dark matter, the peak frequency is a little bit too high, which we show that in this magenta, this pink one. So the peak frequency is a little bit too high, so it's kind of hard to fit the signal for those lower frequency bins. So, so in the next 5 to 10 minutes, I want to switch the gear and talk about another possibility. So I want to talk about the possibility that the dark matter is not particle dark matter, rather is the remnants from the phase transition. So the dark matter is actually primordial black holes. So yeah, again, what if dark matter is not even a particle? So they may be fossil of early universe, not a new sector. So here I talk a little bit about primordial black holes. So they are not normal black holes. They are not from the collapse of stars running out of fuel. Rather, they are from soon after the Big Bang. So they are interesting because they can be a natural dark matter candidate. They can be seeds for supermassive black holes, and there are all kinds of black hole formations being discussed in the literature. So I'm going to show you the possibility that they are from strong first order phase transitions. So the idea is pretty simple. So here we have a scalar field, and we have a scalar potential here. So we just write down a scalar potential for a strong first order phase transition. And we also include some fermion field, and we add some interactions. So early on, at high temperature, the universe is in the symmetric phase. So in this plot, the white region is the symmetric phase, and the blue region is the broken phase. And the red points are matter, the green points are dark matter. And as the universe cools down, there is a strong first order phase transition. So we start to have those blue bubbles being nucleated, and they expand. So the key point here is that if the fermion gets a mass that is much larger than the phase transition temperature, so the new fermions here, they will gain mass during the phase transition through this interaction. So by energy conservation, if this mass is much larger compared to the phase transition temperature, then the fermions cannot penetrate into the true vacuum, rather they will be stacked in the old vacuum. So the fermions are trapped in the old vacuum. And then for a given region of the false vacuum, we can calculate the energy density in that region. And if the corresponding Schwarzschild radius is larger than the actual radius of the region, then we expect the false vacuum collapse into a primordial black hole. So so the whole story is like this. We have a first order, so early on, we're in the false vacuum, and there is strong first order phase transition happens. So bubbles being nucleated and expand. the fermions are trapped in those old vacuum. They keep shrinking with the fermions trapped inside. They may collapse. Those old vacua may collapse into primordial black holes. But there is a obvious problem in this scenario, that is we have particles and antiparticles trapped together in those old vacuum. And since they are trapped together, they will annihilate. So there are several possible ways out. The first solution is that we make the interaction very, very weak, so the annihilation is highly suppressed. And in this work, we engineer some leptogenesis-like scenario to generate an asymmetry between particles and antiparticles. So then we can suppress the annihilation. So now we can again talk about possible probes. Again, we have first order phase transition. So we expect this scenario can be probed by gravitational wave interferometers. And then we have some new fermions. They can be probed by collider. So here we plot the plot the pair production cross section. So they're not small. And how we probe them on colliders depends on how they decay. So depending on different decay channels, we may expect multi-jet, multi-lepton, monojet displaced vortex signals on colliders. And this time we also have primordial black holes, so we can probe them through Hawking radiation by the upcoming gamma ray observatories. So here in this work, the authors calculate the sensitivity for future the sensitivity of using the future gamma ray observatories to probe primordial black holes. And for us, we expect signal in this pink band, so they can be probed by upcoming gamma ray observatories. So now let me conclude. So in the first part, I have shown that the dark matter relic abundance depends on the thermal history, and phase transitions can significantly modify this history, and that expands the space of the viable dark matter scenarios. And those scenarios are testable across multiple probes, including gravitational wave interferometers, collider experiments, and dark matter experiments. And for the other scenario, I talk about the phase transition can also lead to primordial black hole formations. And in this case, we don't need a particle dark matter. Rather, the primordial black holes can assist the dark matter abundance we observed today. So I think the takeaway here is that the phase transitions offers new mechanisms for producing dark matter production, setting the correct relic abundance, and new